Welcome to today's webinar. The topic today is Model and Design Aluminum Structures in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal software company. For instance, the Dlubal website, German and English webinars, press releases, etc. I will be the moderator today. I will also answer your questions together with Thomas Günther. He will support me. He is responsible for customer support in our company. The presentation or the presentator is Sonja von Bloh. She is responsible for the aluminum add-on and our section and for customer support. So you can ask questions via the control panel on the right side of your screen. You can enter a question here and we will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other option is to watch the complete webinar and then email your questions to info@dlubal.com after the webinar. So I hide my webcam that you can see the full screen. I come to the agenda. First point is create an aluminum structure using dynamic blocks. Then load input and combinatorics. Then the design of the structure according to Eurocode 9. And the printout report documentation. Maybe another hint, the webinar will be recorded. I can show you at the end of the webinar where you can find the recording in the next days and the model file and the other files that Sonja will use. Then I hand over the screen to Sonja. Just a moment. Okay, Sonja, it's your turn.
Thank you, Andreas. I would also like to welcome you to today's webinar. This construction can be modeled by entering objects in graphic or tabular form directly in RFEM. This has already been shown in detail in previous webinars. In addition, there's also the option of saving object groups as a block and then reusing this block. In RFEM, 3 block types are distinguished. These are the non-parametric blocks, the parametric blocks, and blocks with JavaScript. I would like to introduce you to all 3 block types. In the case of a non-parametric block, the structure has been created without parameters. The model that you see here was created this way. Here, the node coordinates are defined by values. No formulas are used. In order to save the structure or partial structure as a block, it must first be selected. I want to save the entire structure as a block, so I select the entire structure. Then I go to File and then Save as block. Here I have to enter the name and I have also the possibility to do a classification. The classification is used as a filter so that I can find the block more easily. A few categories have already been created. Here I choose the category beams. The block can now be inserted into any file. I insert the block into the same file. For this, I open the Dlubal Center blocks that manages these blocks. Here are many blocks included. You can see here the beams, then you can use the tower and masts. and so on for your daily work. I first switch to the filter in which I saved the block, and then I select the block. I find it here. Then I go to OK. In the main tab, I can set the insert point of the block by choosing the node in the graphic, or I can choose the node in the drop-down here. And then I can define the position of the insert point. If I write here the coordinates, and I have also the possibility to pick this coordinate in RFEM work window. In the Structure tab, I can change the material, the section, and nodal support. This information was read from the construction, which I saved as a block. If I want to change the section, for example, then I can click on the 3 points here. This opens our section database, and I can use any section that's included in this database. I now click on OK, and the block will be inserted in the file. The block reference is not lost. I can edit or convert the block to normal geometry. I find the block here in Special Objects blocks without parameter, and if I want to edit this block, then I choose the Edit button, and here I can edit the coordinates or the structure. If I change here the coordinates to 15 meters, then the block will be moved. You see this here. There's also the possibility to use the function directly in RFEM. You can move this block by drag and drop. That's all to the blocks without parameters. In the case of a parametric block, the construction has been entered in such a way that the structure depends on parameters. I've prepared such a model that you can see here. In addition to the geometry, loads can also be parameterized. The parameters can be set in the global parameters window. Here I have already created the lengths A, H1, H2, L1, L2, and L3. They have the unit group lengths, but I can choose another unit group as well. Here you have forces and moments and so on if you want to use parameters for forces or for loads. Then I've selected the definition type value. You have here also the possibility to use formulas. I have defined the coordinates using this parameters via a formula. You can open the formula if you click on this symbol here. And here you can see the node coordinate y is calculated as minus L1, minus L2, minus L3. If I now change the parameter, then the structure will be changed. I can change it also back. If I now want to save this structure as a block, I have to select the structure again. I want to save the entire structure, so I select the entire structure. Then I go to File, Save as Block, give him the name with parameter and also the model category beams. Click on OK. And then I will insert this block into this file. For this, I open the Dlubal Center blocks. And in the filter beams, I find this block. And in the main tab, I can do the same things like in the other block. I can choose the insertion point. And then I go to the structure. Here I have the same possibilities like in the other block. I can choose the material, the cross-section and the nodal support. But in addition, I have also the global parameters that I have defined in the structure before. And here I can change these lengths as I want to. I click on OK, and the mapping to the global parameters is lost. If I insert this into the file, I can see this if I change the global parameters. Click on OK. Then only the structure with the global parameters will be changed. Not the structure that I've saved as a block, but you have also the possibility to edit the block parameters in the structure tab. In addition, it's also possible to assign the global parameters to the block parameters. If I define it here as equal A equal H1 equal H2 equal H3, oh sorry, L1 equal L2 and equal L3. If I now change the parameters, in both structures, the parameters will change. However, with the parametric block, it's not possible to add or delete structure objects within this block. If I saved the canopy as a block with 4 columns, as in the example, I cannot add a 5th column within the block. I can add this in RFEM, of course, but this possibility to create dynamic blocks is possible with blocks that use JavaScript. This brings me to the third block type, blocks with JavaScript. With scripting, I can create the topology, the load cases, and the loads. For the creation of script files, you only need an editor like Notepad++. I created a JavaScript file to generate the canopy presented earlier. The 3 main functions, global parameters, input data, and generate, are available for defining blocks. I only used the input data that you can see here and the generate function. in my script. The global parameter function is not used in my script file. The global parameters function is used to create global parameters, which, as I have already shown, can also be used in the blocks. The input data function is used to create the input table in the block dialog with input parameters. Here I show this function. In the input data function, a category can be created in the blocks input table using the category function. This is this here. Here I've created the categories basic data, geometry, supports, and sections. In the basic data category, I then use the parameter int, this is here, function to create an input parameter n, here, of type integer. This is used to dynamically generate the number of base. In the category geometry, I create the input parameters A, H1, H2, and L with the function parameter float. The parameter L is created dynamically via the multiplicity counter key n. This is this here, which I defined above in the parameter int. The function generate is used to generate blocks. Input variables added in the input data function can be used in this function. A list of the available objects and attributes can be found in the console via the info that you can open here in View Console. And if you click here on info, then you can see the object properties. Here maybe member hinges with a description. The nodes are created here. Also the members and the supports, the nodal supports. And here I also create in this function generate the dimension here with linear dimension. A documentation on the blocks with JavaScript will be available later on GitHub. To create the block, the function for creating a block can now be called in any RFEM file. The file content is only used to create the image in the Dlubal Center blocks and has no other function. I first go to File, Save as block, and then I call this block with JavaScript. I choose the model category beams, and here I have to choose the JavaScript file. Then I click on OK. If I now open the block, you have also the same option in the main tab, And in the Structure tab, you have here the number of base n. And here I have predefined 3. That means you have 3 base lengths that you can see here, L1, L2, L3. And to make this dynamic, I can choose here also 5. And then you can see this has changed to input L1, L2, L3, L4, L5. Okay. This brings me to the creation of the model of the webinar. I close this file and I create a new one with File New. In tab Main, I define the model name with Webinar. I choose type of model 3D, and then I go to the tab Add-ons. Here I can select the add-ons that I want to use in my model. A green dot in front of the add-on indicates that a license is currently available for it. An orange or blue dot indicates that the add-on can only be used in demo mode or as a trial version. I select the aluminum design, and the 2 checkboxes, Combination Wizard and Load Wizard, are activated by default. This uses the Combination Wizard and the Load Wizard to combine load cases and to generate wind and snow loads. Then I go to the Standard tab. Here I specify the standards for the load case classification. I have here several standard groups for my choice. Here I select the Eurocode 1990 and the national annex from Germany. For the load method, you have also several standard groups, and here I also select the German national annex. For the design of aluminum, I have 2 possibilities. I can use the Eurocode or the American standard ADM. Here I want to show the Eurocode also with national annex from Germany. General information such as acceleration of gravity and tolerances can be specified in the Settings and Options tab. Here I activate the member representatives. A member representative is a sample member with identical properties. The settings for the member representatives can then be made in the member representatives wizard. RFEM checks all members for similarities with regard to the activated criteria and outputs the result as a list. I can then assign properties such as effective length via the member representative, which defines these properties for all members of this member representative. This means I don't have to assign these properties to each member individually. Furthermore, I can easily find members with the same properties via the member representatives. Then I go to the tab Model Parameters. Here the geographic position of the model can be specified and information about the model can be entered. I want to assign a location here. To do this, I click on the 3 dots here. And here I have to enter the location. I choose our company headquarters. That's located Zellweg 2 in Tiefenbach. And then I can confirm my choices with OK. And the load wizard for snow loads and for wind loads then uses the load values of the specified location. And I click on OK. This will create a new file. And to create the model, I insert the block I created earlier. For this, I open again the Dlubal Center blocks, go to the filter beams, and choose my block with JavaScript. I then click on OK. I choose the insertion point numbers 16, and I define the x coordinate in 2 meters. Then I go to the Structure tab. Here I choose a different nodal support. Here I choose this type. And for the purlins, I choose a different cross-section. The model has been created so far, so that I can now create the load cases. The load case LC1 is automatically generated. That's a load case self-weight. And the active self-weight checkbox is already activated here, so that the self-weight of the structure is automatically generated as a load. In the static analysis setting here, I can select which calculation theory should be used to analyze the load cases. Analysis types are already preset for this. Here I have the analysis according to first order, second order, and third order. If I don't find the static analysis settings that I want to use, I can create a new one, or I can edit the settings here in the Edit Static Analysis Settings tab window. Here I choose geometrically linear. The action category that you can see here is important for the superposition. The partial safety factors and combination factors are stored in it. Here I choose permanent. Then I click on OK, and I want to define an additional load. To do this, I create a new surface load. For this, I go to the load wizard, and I want to use the member loads from area loads. This load wizard simplifies the task of creating a surface load on members of the model. You can use this to apply a load to the purlins without manually determining the load distribution on each member. Here I go on New Load Wizard, and in the main tab I define the load parameters first. Here I define the load distribution uniform, coordinate system global, load direction is okay also, and here the node magnitude should be 0.15 kilonewton per square meter. Then I go to the next tab, and here I have to define the load plane. For this, I click or I select the corner nodes in the graphics with this function. And then I click on OK. Furthermore, I can specify here which member should be excluded from the load application. Here I choose members parallel to the beam. And then I click on OK. The load can also be displayed separately with this function display separately for control purposes. Here you can see the load distribution. Okay, the load is okay. And then I define the next load case. Here with new load case, I want to define a snow load. So I give this load case the name snow. Then action category should be snow. And then I click on OK. For this load generation, I also use a load wizard, and here we have the load wizard snow load. This load wizard simplifies the task of creating snow loads on members of the model in accordance with standards. So I create here the new snow load, and in tab main I have to choose which roof type I have. Here I have the choice between flat and monopitch and dual pitch roof. I have a flat or monopitch roof, so I choose this option. Then I have to define the roof corner nodes. And then I don't want to apply the loads on the beams, so I select this beam. Then I go to the parameters. The parameter of the snow load have to be defined here. Since I have already selected the location and the model parameters, the parameters have already been taken from this. You can see this here. I have my location and the location and the altitude, load zone and so on are taken from this location. Furthermore, I can activate additional options such as snow overhang or snow guard or something like this, but unfortunately these functions are not yet finished. But I wanted to also consider a snow overhang, so I will define this manually. Then I click on OK. I can also show this load separately, and then I define my snow overhang with a new member load. For this, I change the load direction to global and Z on projected length, and I define here the load magnitude. This should be 0.537 kilonewton per meter, and then I choose the member where this load should be applied on, and I click on OK. Snow load is ready, is finished, so I have to define wind loads, and if a canopy roof like this should be designed, a load determination with regard to section 7.3 of Eurocode 1991-14 is required. We have only load wizard for closed buildings that you can see here. That's here the load wizard for windloads, but they are only for closed buildings. So I have to apply the load manually or with the help of AirWind. How to determine the load manually is described in the knowledge base article. I want to show you this article here. On our homepage on dlubal.com, you have here the tab Support and Learning, and you can find many knowledge base articles here or frequently asked questions here. And in this article, it's described how to determine wind loads for canopy roof structures. Okay. Go back to the program, and then I have to create my wind load cases. As an example, I only create the wind pressure and wind suction in +x direction. According to the standard, further flow direction and frictional forces according to section 7.5 would have to be taken into account, but I'm neglecting it here. So I create a new load case. Wind pressure in +x with action category wind. And then I click on OK. Then I use the load wizard member loads from area load. And here I choose the load distribution varying in x. And I want to apply the load perpendicular to the load plane. So I choose here local Z. And then I go to the tab varying. Here I have to define the area load parameters. I've calculated it before with Excel according to the technical article I've shown you before. And here I copy the load parameters and paste them here. Then in the geometry tab, I have to define the boundary of the area load plane. For this, I choose my 4 corner nodes. Click on OK. And I don't want that the load is applied on the members, so I select the member and then I click on OK. I can also show the load here as area load. Here you can see the parabolic distribution of this load. The second load is the wind suction in +x direction. For this, I copy the wind pressure in +x direction. I rename this load case. This is now wind suction. Click on OK. And I only have to change the parameters in the member loads in tab varying. For this, I copy the wind suction parameters. And click on OK. OK. Wind loads are finished. In a stability analysis, I determined that the influences from second order theory must be taken into account. How such a stability analysis can be done has already been shown in previous webinars. So I have to generate load combinations according to the second order theory, and I have to apply global imperfections. For this, I create the imperfection case, imperfection n plus x. We go here to imperfection and then new imperfection case. This should be my imperfection in plus x. Here I choose the imperfection type local imperfection. There are many more imperfection types. And the option assigned to all load combinations without assigned imperfection case is already activated. This ensures that the imperfection case is taken into account for all load combinations that are not entered manually in the assignment tab. Here in the assignment tab I can see the generated load combinations with imperfection, and furthermore you can assign the imperfection case to specific load cases and combinations. For example, if only the imperfection case, imperfection n plus x, with the load case wind suction in plus x is to be taken into account, then I have to move this load by double-clicking it to the assigned object, and then I have to deactivate the checkbox, and now I see the results. It's much smaller. I don't want to do this today. I want to assign this imperfection to all load combinations, so I activate the checkbox again. Okay, now I have to define the local imperfection. For this I create a new member imperfection. I choose the members where I want to apply the imperfections. And then I have to choose the imperfection type. Here you have the possibilities: initial sway, bow, and so on. I choose here initial sway, and you have many definition types. I want to define the imperfection according to a standard, so I choose the standard, and I have to define the imperfection direction. If you want to see the directions, you can click here on this button and then you can see the result. And I want to assign this imperfection in plus x direction. This is the local z direction here in this case. Then I have to define the structure height. I will measure that from the column. And the number of columns in one row is 1 in this direction. So I click on OK, and the imperfection is created. I can show this with this button here. The other imperfection will be created by copying this imperfection. So I click here on copy selected imperfection, it's the imperfection in minus x direction. I click on OK. Then I only have to change my imperfection direction to minus z. Here I can see the results. Then I need an imperfection in plus y. Here I have the imperfection direction y, and in this direction I have 4 columns, so I choose here 4 and click on OK. Last imperfection is the imperfection in minus y. Okay. Okay. Now the imperfections are complete, my load cases are complete, and so I can make settings for the combinatorics. For this, I go to the load cases and combinatorics, to the combination wizard. I'm defining here the second order analysis, and then I activate the checkbox generate same load combination without imperfection case, and that's all what I want to do here. Okay. Furthermore, I make settings for the actions. For this, I open the Action tab, and the action category corresponds to the category of the corresponding load case. For action category permanent, I have here assigned the self-weight. For the snow loads, the snow. For the wind loads, the wind. And in the action type, this controls how the load cases of the action are taken into account in the superposition. Here you have the possibility to use the action type simultaneously if they can act in if the wind loads can act in the same load combination, or alternatively if they don't act together, and they don't act together, so I choose this option here. Then I go to design situation. The standards describe how the actions are to be combined. And also Eurocode 1990 requires designs of the ultimate limit state and the serviceability limit states, for which specific combination rules apply. This is considered in the program 2 for design situation that you can see here are automatically generated by default. However, I can also add other design situations. If I click here on this button, create new design situation, and I can also choose the design situation type that I want to use. And on the info button, you get information of the combination rules of this design situation type. Okay. Then I go to load combination. That generates my load combination here. Static analysis settings are second order. That's what I wanted to have. So the combinatorics are okay now. So I click on OK, and then I have to make my aluminum settings. And this I want to do with the member representatives, and RFEM has detected 3 member representatives. These member representatives are colored with this quadratic symbol here. It's here the green one, the red one, and the blue one. And these are the columns, the beams, and the purlins. I can give this member representatives also a name. And so I double click on this member representatives. I can give them a name. I name this member representative columns. And the first one, I name it members. And the third, purlins. Okay, then I go to the tab design types. Here I have the possibility to define effective lengths, local section reductions, shear panels, and rotational restraints. And first I create a type for the effective length for the design of the columns. For this I click on create new effective length. First, it must be specified which forms of stability failure exist for the member. According to Eurocode 9, the possibility of torsional or lateral torsional buckling for hollow sections can be neglected, so I deactivate the checkboxes torsional buckling and lateral torsional buckling. However, these checks are not performed by default. On the ultimate configuration, I can also make other settings for this. I will show the ultimate configuration later. Then I go to tab nodal supports and effective lengths. Here I define my nodal supports and the effective length factors. This is okay. And I'll start by looking at the ultimate configuration in the design configuration tab. Here I go to edit and I name this ultimate configuration to columns. And here the stability design checks are activated. Here you have the possibility to define alternative values that are described in the standard, or here you have the possibility to perform the design for sections like hollow section that I mentioned before if you activate this checkbox. Okay, go on OK. If no design configuration is assigned to an object to be designed, then no design are carried out in this configuration for this object. I won't I don't want to do a serviceability check of columns, so I don't choose a configuration here. Then only the ultimate configuration will be used, and only the stability checks and cross-section checks will be done. Then I go to member representatives. Here I wanted to name this beams. Oops, beams instead of members. And in this member representative, I don't want to do a stability design, so I create a new ultimate configuration. I go here on, and I name this beams and purlins, and here I deactivate the checkbox perform stability design checks. Then I click on OK. Then I want to see my serviceability configuration. For this, I click on Edit Serviceability Configuration to open this window. And in the serviceability configuration, the limit values to be checked for the design can be specified. The deflection limits are defined as a fraction of the reference length. A distinction is made between the cases of beams and the cases of cantilever here in this section. Okay. Then I go to the tab Design Supports and Deflection. For the aluminum design, the beam type is derived from the defined design supports. If I define a support on both sides of the member, the type is interpreted as beam. If a support is only defined on one member side, the member type is interpreted as cantilever. Depending on the type of beam, the limit values defined in the serviceability are used. Here I have a cantilever, so I only define support on the member start. For this I click on New Design Support, and here I activate the support in Z-axis. You have here the possibility to define the support width and depth. This has no influence on the design. Then I click on OK. Then I choose the check direction. Check should be done only in local axis Z. Displacements reference, you have here two possibilities, should be deformed segment ends, and the design supports also take on the function of segmenting the members for the deflection check. Such design supports can be defined at every intermediate nodes of the member. Depending on the location, you can use this here to check different reference lengths for determining the permissible deflection. But I don't have a node here on this member, so I don't use this. Then I go to the member representative purlins. Here I go to design configuration. I want to use design configuration beams and purlins, as I don't want to do a stability check here. And I use the same serviceability configuration. Then I go to the design supports, and deflection, and this design, the purlins are have supports on both sides of the member, so I use the same design support that I created before. Okay, then I choose also the check direction local axis Z, and I think, okay, now I've defined all things here. All types for aluminum design can be represented also graphically. For this, I open the navigator display, and here you can see the types for aluminum design. Here you have several possibilities. You can see the member effective length graphically if you activate this checkbox. You can see that's here. Or you can see the member supports or design supports here. Okay. This allows easy checking of the correct assignment and clear documentation of the graphic printout. I would like the other settings in the table. For this, I enlarge the table a little bit. Here you have the possibility to choose the table structure, imperfection, and so on. And you have also a filter for aluminum design. This shows the tabs for the design situations and objects to design. And in the design situations, here in this table are listed all design situations that are listed in the model. Here you can decide whether and how a specific design situation should be taken into account for the aluminum design. I only want to check the design situation, the first and the second. The other one I don't want to check, so I uncheck the checkboxes. Here you have also the possibility to choose a different design situation type if you want to. Then I go to Objects to Design. All object types on the model and suitable for design and the add-ons are listed as one row in this table. And by entering an object number in the cell removed from design, you can exclude certain objects from the design. I only want to design the member representative, so I deactivate this checkbox. So all inputs are ready, so I can start my calculation. For this, I click on Calculate All. After the calculation, you can choose navigator results if you want to see the static analysis results or the aluminum design results. If you choose here the entry, and here you can see the design checks graphically. The design checks are also outputted in tabular form. For this, I choose here aluminum design, and here you have many possibilities. Here you can see the governing results or design ratios on member representatives. You have several tabs, design ratios by design situation or by loading or by material. And you can open the details of the design if you double click on an entry on the table, and here you can see all details of the design, also with formulas, and here you can see this member is characterized as cantilever, and you can see here the design check. Further detailed graphics are also available if you click on diagram and section. Here you can choose the stresses, and then you can see the stresses on the section. And it's also possible to show the result diagrams for the static analysis and for the aluminum design. Here you can choose which member representative should be displayed here in the tab. Yeah. Finally, I would like to show you the documentation. The aluminum design add-on is fully integrated into the main program. The function of the printout report are therefore available for documenting the input data and results. For this, I go to the navigator data, and then I create a new printout report. And in the list, you can choose which topic should be included in the printout report. Here, I activate all, then I deactivate it. I only want to print the aluminum design topics in the printout report, so I check these topics. Here I have additional filter options, and then I click on Save and Show, and then the printout opens. And here you have the results in tabular form. It's also possible to print graphics to the printout report. For this, I go to Print Graphics to Printout Report, and then I can do the settings in this window. For the graphic picture, I want to rotate this graphic, so I choose here a rotation. Mm, 270 degrees, and then I click on Save and Show. With the documentation, I have now come to the end of my presentation. I now give the floor back to Andreas.
Okay, thank you, Sonja, for the nice presentation and complete presentation. We are a little bit over the time, but I would like to show you where you can find the recording and the models and files of the webinar. Just take a look at my screen. Under www.dlubal.com you can find under news and events the webinars, and that is where's today's webinar? Let me find it. Here, okay. It's a little bit at the bottom because now it's over. You will get a link to that page here. You don't have to search it, and the recording will be here in the middle, and here under the presentation slides you will find the model and the Excel file and the script. Okay, then at the end I will thank you for your attention. Thank you to Sonja for the presentation, to Thomas for answering the questions. I wish all a nice rest of the day. Yeah, and bye-bye.
Bye.